Hello, here we go. Part 2, solving logarithmic equations.
Okay, so we're going to do it in a Cockney accent today. I hope you can understand us very well. So, here we go. No, seriously. To solve a logarithmic equation. First, determine the acceptable domain. Second, isolate the logarithm term on one side of the equation. You may need to combine terms first using some of our properties. Third, write the equation in exponential form or raise the base to the side of the equation. You'll understand that later. And solve for the variable. So, here we go. Number 1, natural log of x equals 10. The first thing we have to do is domain. So, notice that that thing following natural log has to be positive. In this case, it is x. So x
is bigger than 0.
Now we go to solve this. Now notice one side has natural log and the other side doesn't. So to do this we need to think about the fact that we can convert this to an exponential equation. Okay, remember logarithm is exponent. So our exponent is 10 on the base of e and that is equal to x. And guess what? That's all you can do. So if you get this on the non-calculator portion of the test, this is how we want it. If you get it on the calculator portion, if you wanted to, you could figure out, you could write down that e to the 10 is about 22,026, which, if you look back up at the top, our domain, x had to be bigger than 0, and it clearly is.
All right, the next one. Here we have a logarithm on one side and no logs on the other side, and this is just 1. There's no like plus 5 or anything around it. So let's just go ahead. Let's find the domain. All right, so 5 minus x has to be greater than 0. So let's solve the inequality. Negative x is greater than negative 5, so x is less than 5, because when you divide by a negative, you have to flip the sign. So x has to be less than 5. Now, to get this by itself, what I'm going to do is I'm going to go ahead and take it out of logarithmic form and put it into exponential form. So I'm going to do my ear trick. So I've got 3 squared equals 5 minus x. Well, now I have 9 equals 5 minus x. Subtract 5 from both sides. 4 equals negative x, so x equals negative 4. Is negative 4 less than 5? You betcha. So this is a good answer.
Yep. And that's that. Okay, now here we've got a domain issue that we have to take care of first. Okay, the only thing is the 4x, which must be positive, and we get x has to be positive. So now when we see this, notice that 3 is just a constant, so we're going to go ahead and move that to the right-hand side of the equation.
Solve for the log. Get the log by itself. So subtract 3. I'm going to go ahead and rewrite it.
So 2 log, okay.
So now we have 2 log of 4x equals 4. So now we have to get the log by itself, so let's divide both sides by 2. So log of 4x, oops, need that parentheses there, equals 2. So now we can go ahead and get it out of logarithmic form into exponential form. So I'm going to do my ear trick. The base on a log, since it's a common log, there's no base seen, so I understand that it's 10. 10 squared equals 4x, so that's 100 equals 4x. So x equals 25.
And once again, check your domain, and it fits.
So this is a solution.
Okay, the next one, if we look at this one, we can see that both of the arguments, that's what that thing is called that's in the parentheses. When we say function of something, the thing that follows of is called the argument in mathematics. The argument in both of those is the same. So we really just have to deal with 2x plus 1 being positive for our domain. So that's 2x greater than negative 1, so x has to be greater than negative 1/2. Now, if we look at this, notice that we have log on both sides. So let's just do basic algebra, and let's take the one on the right-hand side and add it to the one on the left-hand side. So that gives us 2 natural log of 2x plus 1 equals 8.
Okay.
And then, again, that 2 could become an exponent, but it's so much easier to divide both sides by the 2. So we get natural log of 2x plus 1 is 4. And now let's go ahead and write this exponentially. So I have e to the 4th equals 2x plus 1. And now we're doing basic algebra to subtract the 1 equals 2x. And let's write this as 1/2 times parentheses e to the 4th minus 1. Now, it turns out that that is about... That's a 1, yeah. That is about 26.799, which does fall into our category of
greater than
negative 1/2.
So now we have this situation where our logarithms they're two different arguments, okay? So we need to actually look at the intersection of these two domains.
We did stuff like that back in the fall, so
let's look at what happens for this one. X plus 1 has to be greater than 0, so x has to be greater than negative 1. And this one says x minus 2 has to be greater than 0, so x has to be greater than 2.
Now this is an AND argument that we have to consider. So we need to look at the overlap. So let's just kind of sketch these on a number line. Okay, so we have the one that's greater than negative 1. It's that one. And then the one that's greater than 2. Now, where do they overlap?
Over here, greater than 2.
So our domain is x must be greater than 2. That's what we have to look for. All right, now let's look back up at the problem. You can see if we have log rules. Remember all those rules you learned? This plus here means multiply, so let's go straight to the next step and write log of x plus 1 times x minus 2 equals 1.
That's all in parentheses because that's all in the log.
Equals 1. We have used our property of adding logs means multiplying the argument. Now, notice our base is 10, so 10 to the 1 equals x plus 1 times x minus 2. Now we're just looking at a basic algebra problem. Remember that when we have something like this, we must first of all set it equal to 0, so we need to go ahead and FOIL out the right-hand side, and that's equal to 10, so now setting it equal to 0 gives us 0 equals x squared minus x minus 12. Okay, she's in her Algebra 1 mind here.
It's a B day right now.
It's a B day. So. It's an Algebra 1 day. Okay, now if you look at that, we factor that very easily. X minus 4x plus 3. And you can see that the solutions to that would be x equals 4 or x equals negative 3, but
x equals negative 3 is not in the domain. So that is not a solution.
So our answer is x is equal to 4. Now let's look at the graph of this because it says to show it graphically. And this is one of the reasons we wanted to show this to you is if you're not really aware of what should be happening, your calculator can lie to you.
It would tell you, see, here's the solution at x equals negative 3, and here's the solution at x equals 4. So by the graph, it looks pretty nice. But if you remember, we had two logarithms. The calculator doesn't realize that we have two logarithms. So it's going to not exclude the other one, so it's not taking each one into consideration.
Yeah, it's not looking at them separately, and that's a really important thing because of the original way you got this problem.
Okay. Okay. So go ahead and do number 35 and 40 in your textbook for chapter 5-6.
Yay!
Okay, here's the next one. Notice that we have three logarithms, so we need to check the domain for all three. So we have 4x minus 1 has to be greater than 0. So we've got x is greater than negative, positive 1/4,
yeah.
sorry.
Yeah.
X is greater than positive 1/4. All right, we have x plus 2 is greater than 0, so x is greater than negative 2, and x has to be greater than 0. So where do they overlap? Well, if we look at, do we need a number line?
I think you could. Yeah, I think we could see pretty quickly that it's got to be
greater than 1/4.
So we're going to write. That's what our domain is. Your domain is that x must be greater than 1/4. That's from that point on. All three of these overlap. That's what you're looking for. Okay, so here we go. Let's do the first thing. If you look up here, the first thing we can do is we have that little plus sign there. So let's make this a multiplication. ln of 4x minus 1 times x plus 2 equals 2 ln x. Well, what's that 2 on the ln x do?
It's really an exponent.
Ah, so that becomes ln x squared. The other side, just leave the other side like it is, because now we have an interesting situation we haven't had before. Notice on both sides we see natural log. Now, we're not going to divide by natural log because that is a function and you can't multiply, divide, you can't do that. However, we can do something called take the anti-log of both sides, which basically means undo it.
So raise both sides to the e. So it would be e to the ln of 4x minus 1 x plus 2 equals e to the ln of x squared. Now remember, we talked about e and ln are inverse functions. So e to the ln is actually whatever this stuff is inside. So this is 4x minus 1 times x plus 2 equals x squared.
And that was the part of the instructions on the steps that I said you would understand it later. This was here. Now let's do the algebra that we need to do. Oh, we have a graph, I think, somewhere.
No, we don't.
Oh, okay, we don't have a graph on that. Never mind. All right, so we're going to FOIL the left side, so that gives us 4x squared plus 7x minus 2. And the right side is equal to x squared. So if we set this equal to 0, we get 3x squared plus 7x minus 2 equals 0. All right, we're just going to tell you it does not factor. So by using quadratic formula, you eventually get this, negative 7 plus square root of 73 over 6. We leave it to you to get that far, but go ahead.
The reason that we don't have the plus minus is because the minus wouldn't be in our domain.
Yes. A negative 7 minus a number is already super negative. So that is our answer. And it turns out that this is going to be about, this is kind of cool, 0.257. And that is barely, but it is bigger than 1/4.
All right, so you got to check those. All right, so here's a word problem. If $8,000 is to be...
Do I not have that one?
No.
I guess I left that one off.
All right, if $8,000 is to be invested at 6% per year compounded monthly, how many years will the investment be worth? 22,520. Okay. So, we have the equation for compound interest, A equals P times 1 plus R over N to the NT. All right.
Oh, gee, you remember doing those very recently? Yes.
Yeah, they were on the test.
And what we had to do recently is, in the past, you only knew how to graph it and make one of the, and solve this and find that value. But the thing is, now we're going to show you how to algebraically do it. And this is what you have to do when you do these calculator problems. Yes, you'll use a calculator to get to the very end answer, but not until you get to the very end. You must show all of the algebra.
Okay, if $8,000, that's our principal, so we have P equals 8,000. Is to be invested at 6% per year, our rate equals 0.06. Compounded monthly, so the times it's compounded yearly is 12 times because there's 12 months in a year. How many years will the investment be worth? 22,000. So we're solving for T, we don't know, and we want an A needs to be 22,520. So now we have 22,520 equals 8,000 times 1 plus 0.06 over 12. Raised to the 12t. Now, first things first, got to get the exponent stuff by itself, so we're going to divide by 8,000.
So show this
22,520 divided by 8,000 equals 1 plus 0.06 over 12, which is really 0.005. Oops.
Yeah, let's do that.
Equals 1 plus 0.005 to the 12t.
And it turns out that in this problem, 22,520 over 8,000 becomes a nice number, but in the event that it doesn't reduce to something that's a terminal decimal like that, then you need to keep that stored value in your calculator. So this reduces, notice we are solving for the variable which is an exponent, and that is why we have logarithms. We can take the log of both sides, and I'm lazy, so let's do natural log.
So notice that we have the exponent thing all by itself. All right, so that's when we can take the natural log of both sides. So ln of 2.851 equals ln of 1 plus 0.005 to the 12t.
She meant 2.815, but it's what she wrote.
There.
Yep. And then that allows you to bring down the exponent. Okay, so we have nothing on the left-hand side changes. On the right-hand side, we get 12t times natural log of 1.1005 is what that becomes.
All right, now we can just divide by the natural log, because this is just a number, remember. So now we get ln of 2.815 divided by...
Can we divide by the 12 at the same time?
Oh, and the 12, so we'll divide by 12 ln. Let me move that. 12 ln of 1.005 equals t.
And that is now calculator ready. So if you saw this on non-calculator part of the test, this is how you would leave it.
Well, you'd probably leave it with fractions.
Yeah, you probably would leave it with the fractions. But this is how far you must get before you do the calculator work. So we get t to be 17.292. So the answer to the question, how long will it take to get to 22,500? About 17.3 years.
Okay. All right, so we're talking about rabbits now. And a certain species of rabbit increases exponentially according to the function, and it gives it to us, where P is the initial population and R is the continuous growth rate. At the beginning of a 12-month study, there were 50 rabbits. At the end of the study, there were 164 rabbits. Write a function for this population. All right, so we have S of t equals P to the ERT.
PE to the RT.
PE to the RT. So,
all right, well, our initial growth rate, our initial amount, P is 50. Okay, R is our growth rate. We don't know that. T is our time passed. And so what we're going to do, and we know that at 12, S of 12 is 164. So what we can do is set the information that we know in the problem, 164 equals 50 E to the 12R.
now this is meaning time is in months, guys.
Yeah, that's right. So we know that N is right there. N is 12 because of this in 12 months. So we're establishing that our time is going to be in months by the way we substituted. Okay, so now we're going to isolate the part with the exponent so we can log both sides. So that'll give us 164 over 50 equals E to the 12R. We're ready to take the natural log of both sides. Natural log of 164 over 50 equals natural log E to the 12R. Now, you should know by now that that natural log E is going to become 1. So this is 12.
The R cut
The R
off.
didn't cut out, yeah.
There we go.
There we go. All right, so what we have is on the right-hand side, left hand stays the same. Right hand says 12R, and that times ln E is 1, so that goes away. And we get R equal to 1/12 of natural log of 164 over 50. And that all comes, when you go to the calculator, you get 0.09899 and a bunch of other numbers, and you want to store that value. Okay? All right, so that is, so the function would actually be S of t.
I'm going to write it right in
Yeah.
here. S of t
Equals 50 E to the
0.0.
0.99 t. Now that's our function that we would use. So that's the answer. That is the answer to answer A. Now the next question is, when will the population reach 1,000? So that's when S of t is 1,000, and we're looking for t. Oh, you are so smart. So we have 1,000 equal to 50 E to the 0.099 t. And once again, isolate the exponential part. So that'll mean, first of all, dividing by 50. And now we're ready to natural log both sides. The whole reason for doing that is so that we can bring that beautiful exponent down. Remember, we are writing this approximated exponent, but you need to have the stored one.
Because we're about to divide by that. Now remember, ln of e is their inverse functions. Since they're inverses, all you get is the exponent. All right, so use the store value when you divide.
So we have t equal, but you have to show us the work, and this is the work we need. ln of 20 over that 0.099. Okay? With the stored value, you get t to be approximately 30.264. Okay, so the question we have is, when is the population going to reach 1,000? And let's remember that we were in months, so in about 30 months. That's just a little over 2 years. And then it says confirm graphically. So when we look at this graphically, you see our exponential function in red, and you see the 1,000 in green, and there it's confirmed graphically.
Okay. Okay, population of a certain bacteria culture at time t is given by this function. How long will it take for the bacteria population to reach 8,000? Well, remember, this is giving us how many bacteria we have in time t is f. So f right there is what we're looking. We've already got this 8,000 stuff.
So we're just going to set it up in the equation. Oh, I will just write. Okay, you're probably going to.
Okay.
We're going to use a lot of space, so you might want to just start from here, and we'll just fill in 8,000 for f of t equals 20,000 over 1 plus 20 e to the negative t over 3. All right, so the first problem we have here is that denominator, so let's multiply both sides by it. So we get 80 times parentheses 1 plus 20 times e to the negative t over 3 equals 20,000. Now, what would we do with that? We're
Divide by 8,000.
Exactly. We're trying to get to that e to the negative t over 3. So we've got it deeply buried. So
it's like one of those teeter-totter tables where you're trying to like get the thing out, you know?
Yeah. So negative t to the third equals, 20,000 over 8,000, and let's just recognize 20. Yeah, that's okay. Go ahead.
20 over 20 over 8.
It becomes 20 over 8. 20,000 over 8,000 becomes that. That's a nicer number. So
No,
what we have is, we have 1 plus.
Well, we can, okay. So 1 plus
20 e to the negative t over 3 is equal to, that's 2.5. Now it's really easy to do that subtraction.
So now divide by 20. E to the negative t over 3 equals 1.5 over 20. So,
now we're ready. Look at that. We've got the term with the exponent completely isolated. So what are we ready to do?
take the natural log of both sides.
There we go.
Okay.
That lets you, the whole reason for that is it lets us bring down that exponent. Times, oh yeah, duh.
All right, now I can go ahead and solve for the t. So we have negative, well, I'm going to go ahead and multiply.
Yeah, let's multiply by negative 3, yeah.
So we've got t equals negative 3 times ln of 1.5 over 20.
And when you plunk that little thing in your calculator, you get t to be approximately 7.7708. So when are we going to get to 8,000? In about 7.8 years.
8 hours?
Hours. Years. Oh, it seems like a year to me today. All right.
Okay, here's your last ET problem, do 47 and 73. And email us one new thing you earned, one good question, and 2 old skills.
We love you. Thanks for being patient.
Bye.
Good job. Good job.